Can you actually like hear me clearly? I guess maybe, or is there some sort of distortion or something?
Yes, sir. Sort of distortion due to your mask.
Nah, that was cheeky, but I don't think it's due to the mask because we're actually having the microphone really close to me. So okay, I'll be a bit louder. Is it better now? Maybe. Yeah.
Yes, it's better only. No problem. You can continue now.
Great, great. Thank you very much. Thank you. Okay. So is there something that you'd like to be discussed today, or we can just go our usual flow, maybe? Uh, do you have any preferences for today's session?
Yes, sir. Oh, we will discuss some techniques, sir.
Yes, I think that that is according to the type of videos that you have watched, right? So do you maybe have some doubts and some problems or something that we could take up before we jump into our regular session?
No doubt, sir.
So we can start as per our regular sessions, right?
Yes, sir. No problem.
That's fine. Okay. Give me a moment, okay? Okay. Uh, so we'll start now, and I would just like to, recapitulate what we've done so far in the last two sessions because I think you both were not there earlier. So this was also, if I'd appreciate it if you keep responding, okay? Because we are only one to one. So I guess it would be more helpful if you keep responding, so I know that you are getting there. Okay, Shashi.
Okay, sir. Okay, no problem.
Thank you. So in the first session, we just um, applied some basic stoichiometric calculations on different types of equations, and you might have also seen them in the videos. But what I did differently was that in the videos you might have seen many equations to calculate different coefficients and all these yields and the productivity and uh, the limiting reactant, the excess reactant, all these things. But we did not use any sort of equations, and we formulated an entirely intuitive paradigm to solve these problems. So that was the thing we did differently. Another problem we took up was the hydrocracking problem, and we did all those stoichiometric coefficients analysis and different productivity and all those things on this problem as well. The third part, we took another complicated reactions, basically a system of two reactions, and a part of that was going, a part of the reactants were entering the first chamber, and another part of the reactants were entering the second chamber or the second pathway. So we did similar calculations with this. And with this, we the first live session was concluded at that point. And this in the second session, what we did was we solved nonlinear algebraic equations using some numerical techniques. Okay, so The first part we did was basically a single variable to equation. For example, this entire equation contains only z. You understand that, right? You can see that.
Yes, sir.
Okay, so this contains only z. Now, the interesting thing here is that we can approach this problem from both the ways. So the first way would be from the left-hand side, you're trying to obtain z as as an inverse square of this entire expression, and then you are successively substituting different values of z based on any initial guess you took. And another approach would be to obtain z from the right-hand side. So you take the 0.4 there, and yes, did you have to say something maybe?
No, sir. No.
Okay, oh, you were, I guess, just agreeing to what were discussing, right? Okay, so you could take the 0.4 right here and then divide everything by 4 and then raise everything to a power of 10. And then what another interesting thing we discussed was how to, take an informed initial guess. Because if you have some random equations like these, so, or maybe a better equation would be this one. Yeah. So if you want to, take a good initial guess, then you need to understand the nature of the problem. For example, if you have a certain equation like this one, you have this, let me just change the color maybe. This one, yeah. No, it did not change. Oh, it changed. Okay. Like this equation. Can you see that? Z equals 10 to the power 1 over 2 square root of z minus 9.8, right? Yes.
Yes, sir. Yes.
Okay. So, so what we are doing to take an informed initial guess, we are just visualizing the both of these graphs, y equals z and y equals this function. So, if you want me to go through this again, then we can do that, or else we can just switch to what we are doing today. What do you say? It's all on you.
Sir, go through these methods shortly.
Okay, go through this method shortly. Okay. So basically, this is what this is I hope you already know about the bisection method, right?
Yes, sir.
Okay. So once you know about the bisection method, and what we are asking you to do is that you solve this equation z equals 10 to the power 1 over 2 root z minus 9.8. And this is actually nothing but uh, another representation of this one. You see this one, right?
Yes, sir.
Now, what I said is that take it here and add here, divide everything by 4, take the 10th power, and then divide it by 10 to the raised to the power 5. So if you, 4 minus 1, so if you actually calculate everything and then take the square as well, right? You're getting this, right?
Yes, sir.
Okay, so here it would be 0.1 and minus 5 would be minus 4.9, and you multiply it by 2 because the 2 power will insert inside, so it will be minus 9.8. So that is how we are getting this one,
Okay.
right? Okay, so now what I was telling, that instead of blindly assuming an initial guess, for example, someone could is likely to assume that, let us call z naught, which is the initial guess, as maybe 5, or maybe z naught could be 4 for you, or maybe I could say z naught is only equal to 1. No one's stopping me to do anything, right?
Yes, sir.
However, the farther away from the actual solution you are, for example, if your real solution lies between 1 and 2, just a symbolic example, and you are taking an initial guess somewhere right here, let's say z equals to 30. So this would mean that the farther away you are initially from your solution, the longer you'll be taking for reaching your accurate solution. Okay. So what I suggest then that whenever you are solving any sort of numerical problems, so you check out both the sides, what type of functions you have. If you have a function like this one, then just visualize both of them in a graph, okay, in a 2D plot. For example, you can plot y equals to z like this, and you can also plot y equals to 10 power 1 over 2 root z minus 9.8 like this. It drops down, really fast, okay? So would you like to learn maybe how to represent this part on a graph without calculations, or you'll be able to do it yourself?
Yes, I can do it.
Okay, that's perfect. So where, if I may ask, where are you pursuing your undergraduate from?
From DY Patil sir in Pune in Maharashtra.
Oh, that's really interesting. Actually, I have one of my junior friends who is also there. So that's great.
Yes, sir.
Maharashtra. It's a good institute, yes. Good. Okay, so I guess you got it, right?
Yes, sir, yes.
And once you get it, this will be the actual solution of your problem. So what you have to do is take an initial guess, like this. For example, now you don't know this, right? You need to find out this. Shashi, you hear me?
Yes, sir.
You need to find out this point, right? The point where both of these curves are intersecting.
Yes, sir, yes.
That is the point where both of these z and this function will have identical values, and you can see that this is the point where they have identical values, right?
Yes, sir.
So you cannot exactly find it through the graphs, or what for are we applying the numerical method, right? We need to find
Mm.
the solution using the numerical method, not the graph. So what you can do here is that since this is z, and this is 10 power 1 over 2 root z minus 9.8. So what you can do is that just put a value, let's say 1, right here into both of these, okay? Then
Okay.
from y equal to z, you'll be getting a value of y equals to 1, right? This point would be 1, 1 comma 1, right? This one.
Mm.
And from this expression, you'll be getting something like 1 over 2 minus 9.8, right?
Yes, sir.
So this will be a really, really small number. You can see that, I guess, 10 minus 9.3, right? This will be something like 0.00000 like this, you know? Are you catching up? Are you getting what I'm saying?
Yes, sir, yes, sir, getting.
Okay. So once you know that at one, z equals to 1, both of these functions, which one is the bigger function? Is it y equal to z, or is it this one?
Y is equals to Z1.
Good. So y equals to z is the greater function. So this representation that we have done is not correct, right? So one would be somewhere like here. You can understand this, right? Because in this area, y equal to z is less than this function, the other function. But when we input z equals to 1 in both of these functions, we get that the second function is actually less, far less than y equals to z. So this means that at y equals to 1, the situation is something like this. This one. You're getting me, right?
Yes, sir.
So this means that our solution, where both of these will be intersecting, would be something less than y equals to, less than z equals to 1. Are we correct, right?
Yes, sir.
So this implies that z equals to 1 is a good initial guess for the problem, right?
Yes, sir.
So that is why we'll be taking z equals to 1 as an initial guess. Or if you want to go further close to the actual solution, you can just try to put z equals to 0.5 in both of these, and you'll see that this one comes out to be 0.5, and this comes out to be 1 over 2 root 0.5 minus 9.8. This is also less than 0.5, but it's not much less. So we could also have z equals 0.5. Or if you want to further refine the initial guess, further get closer to the solution, you can have 0.25, 0.1. You just need to keep calculating uh, how how close to the initial solution you can get. So this was what we did. Any questions, any doubts, maybe? You want to ask something?
No, sir.
No? Okay. And this one was a basic problem on mole concept, so I guess you can do it yourself, right? Limiting reactant and excess reactant.
Okay, sir. Okay.
Okay. So, or would you like me to go through this problem once more?
No, sir. No problem. I have already done it.
Okay. So this was all that we did in the last two sessions. So, hmm. So what we'll be doing here is that, for example, you can actually do this part. Maybe give me a moment again, okay? I'll be
Okay.
writing down the problem. I am not sure why it's not writing. Just yeah, can you see some writing on this page? Maybe. Except these three.
No, sir.
Yes, let me reconnect it. Sorry for the interruption. I'm really sorry about that. So, still not seeing anything?
No, sir.
Oh, I guess it's visible now, right?
Yes, sir. Yes.
Okay, so until till now, what we know is that, for example, you have some kind of equation like fx equals to 0, and the form of fx is nonlinear in nature. So you understand what do you mean by nonlinear, right? So nonlinear is basically anything that is not linear. So that means that fx is something maybe x to the power n, where n is greater than equal to n is greater than 1, you could write. So n might be equal to 2, it might be equal to 3, it might be equal to 4, or you might have transcendental functions like the exponential functions, or you could have trigonometric functions, sine x, cos x. So everything is a part of nonlinear problems. Now, there is another class of problems where you have f1 of xi equals to 0, and another system that you've got is f2 of x of I is equal to 0, where I might be equal to, let's say, 1, 2, 3, 4, or something, whatever. Okay. So this means, for example, if f1 is taken as minus 2x1 plus 3x2 plus 4x3, let's call it square, minus 5x4 cubed equals to 0. And maybe let's include a 4 here. And this is f1. And let's take f2 as, let's not maybe take x1, and we could write 2x2 plus x2 squared plus, let's say, 3x3 plus, let's say, 7x4, not square maybe. Let's, yeah, okay, squared. Okay. And here let's add 2 plus. You see this, right?
Yes, sir.
So if you want to find out a certain x1, x2, x3, x4 solution for this equation, what should we do? So the method of successive substitution, or you could also call it SSM because it's successive substitution method. For this part, this requires you to take out a value of xi, where I could be anything, 1, 2, 3, 4, or anything, and take it out, calculate the value from the first relationship, take out the value. For example, you pick out, let's say, x3, okay? Then you obtain x3 as a function of f of x1, x2, x4, right? You can do that, right? Just take all these terms to the right side and find x3. Yes?
Yes, sir. Yes.
And then they just calculate the value from this first equation and insert this value into the second equation with the original guess. So what you'll have to do is that, remember, all numerical techniques require an initial guess, okay? So you need to tell the technique where would you like to start from. So because this numerical analysis is all a simple, a hit and trial type of thing in the initial parts. So you assume a solution, you try and fit it. If it fits, then good. If it no fits, it does not fit, then what you do, you further try to refine this entire thing to change the solution and then try to fit it again. And until you have reached a certain tolerance limit. For example, tolerance would mean that you are really close. For example, let's call this x vector equals to x1, x2, x3, and x4. When you know that you are really close to the solution, then you stop your algorithm. Okay. So how do you know that you're really close to the solution? You just calculate. For example, you took n steps to reach the xnth vector solution. Then you just calculate the difference between xn minus 1 and xn. And take the magnitude of this entire thing. Okay. Or you could also have it like this for the relative error. You might have heard about it, right? And if this entire thing is less than the tolerance, then you stop. So this much is clear, right?
Yes, sir.
Okay. So do you have a calculator at hand that you could take out maybe?
Yes, sir. I have.
Okay, great. So just take that out and we'll start solving this first problem. For example, let's say which variable do you want to take from the first equation? Is there some random choice you want to make, or I can make the choice myself?
So you can make it.
Okay, thanks for letting me have that opportunity. So, okay, so I would like to write, let's suppose I take x2. Okay, so this would be written as minus 4 plus 2 x1 minus 4 x3 squared plus 5 x4 cubed. Okay, from this first equation, right?
Yes, sir.
Now assume, let's say an initial guess that could be, let's call it maybe 0, 0, 0, and everything 0. That is a reasonable initial guess, right? Because in this part, you cannot visualize these curves. You cannot draw them on a graph, right? Because you have 4 coordinates right here. 1, 2, 3, 4. But our systems can only be extended to the third dimension, that is the z dimension, right? So you can actually make an arbitrary initial guess. So what we are making is right here, a 0 vector, a null vector. So in that case, what do you think in the first iteration? Your x2 Let's call it 1 would be equal to minus 4, right? Is that right?
Yes, sir.
Okay, great. Okay, so now we need to switch to the second iteration. So how do you do that? What we do, wait, are you seeing anything being written? Actually, I'm writing, but it's not writing. Do you see anything?
Mm, no, sir, I'm not seeing anything.
Ah, damn it, I think I'll have to change this entire thing. Yeah, sorry, this is another interruption that we'll have to face for a moment. So, sorry, I'm just reconnecting this thing, okay? Ah, okay. Guess it's working right, okay? Yes. Okay, so now the thing is, uh, you actually have 4 variables, x1, x2, x3, and x4. Sorry for the delay. I hope it does not happen again. This much is fine, right?
Yes, sir.
So you'd actually need to have 4 equations, right? So to solve all these, we need to write 3 more functions for here. Let's say f3 and f4. And f3 could be written as, just you can suggest anything. Maybe x1 minus 4 x2 squared plus. So the numbers do not matter here because we are only doing a representative problem. X4 squared equals to 0. And another equation could be 8 minus x1 plus 1.5 of x2 squared minus, let's say, 2 x3 plus 4 x4. This one is a simpler one, okay? So now what is happening, Shashi, take a look here, okay? This
Okay,
is
sir.
a critical part. So what is happening? So what I am planning to do is that you had an initial guess, let's say, okay? Let's say x vector equal to. So you are not confused that why are we writing this entire thing as a vector, right? Or do you want me to clarify?
Which one, sir?
We are writing this entire thing as a vector, right? X1, X2,
Yes,
X1. So you can understand this why we're writing like this, right? So
yes, yes, sir. Yes.
yes, yes. So it is just a representation, a container representation. So it does not have anything to do with physical reality. So when we are writing something like XYZ, then it is not necessarily, a point in the 3D space. So only when you say that it is a coordinate, XYZ, only then it comes into the 3D space. Else you could have anything here like cat, dog, or beer, right?
Yes, sir.
So this is just a way of representation. It does not have anything to do with vectors, but since vectors are easy to understand, people use this notation. Okay. Okay. So now initially you assumed x naught. Okay. Now what you did using F2, you obtained uh, x21. That is the first iteration, right? You get this, right?
Yes, sir.
So now the solution that you have is x1 naught, x21, x3 1, and x4 no, x3 0 and x4 0, right? This is after the first iteration, right? Is this much clear?
Yes, sir.
Okay. So now you use F3 to obtain x3 after the first iteration, okay? So let's do that, right? So put in here, let's say x1 puts 0, and actually, you did not correct me, but this is F1, okay? Not F2. Make a note here, please, right? We used F1 to calculate x2, right? Yes.
Yes, sir.
So we will be using F2 to calculate x3. So it is not that, I just took x2. You could have taken x1 here.
Mm.
Okay. So you could have also taken x3 here, x4 here. So accordingly, all the variables will be changed here. So from F2, you might be able to calculate x3, but each equation will be used to calculate one unique variable. Okay, so my terminology is that I will use F2 for x3. So if I use F2 for x3, and we'll write x3 is equal to minus 2 x2 squared minus 7 x4. Is it squared? Yes, squared. Yes. Am I right? Right? Am I correct? Right? Divided by 3. This is right. Yes.
Yes, sir.
Okay. So now what you have is that uh, at this stage, the second iteration, x1 is still 0, right? But what is x2? What is x2? This one, right? Yes.
Yes, sir. Yes, yes.
So originally you had taken x2 as 0, but
Mm.
now x2 has become -4.
Mm.
And x4 is still 0, and you need to find x3.
Yes, sir.
Can you do it for me?
Yes,
Just
sir.
calculate x3, please.
-2 4 square minus 7 minus 0 x -2 minus 2 into minus 4 square divided by 3. So it's minus 11.333.
Okay, that's great. 3, let's write this, okay?
Yes, sir.
So we can also, quickly verify this like this. So it's -2 times of 16, that is 32. So that's minus 34 over 3, and that is approximately 1.333, right?
Yes, sir.
You can just quickly verify it. Now, this is x3 after the second iteration, right?
Mm.
Or now, since so this usual method would be that after every equation, you are increasing the number of iteration by 1, right?
Yes, sir.
So this will be cumbersome because every time this will keep increasing, keep increasing. So what we'll do is that we adopt another notation. Now this, what I'm doing, I could have straight away adopted that simple notation, but then there might be a natural question that why aren't we taking it as 2, because this is the second step. So this is why we will not take it as second as 2. So we'll keep it everything as 1, and we'll say that we did all this in a single iteration. Okay. So,
Yes, sir.
and so till the point we reach all the solutions, for example, x1, x2, x3, and x4. So till that time, we'll all call it the first iteration. Okay.
Yes, sir.
Okay. So now let's use our change notation. So at this point, what we have is x naught 0. We've got x2 1 as -4, right? You
Mm.
already calculated x3 1 as -11.333. Now you need to calculate x4 1. And you also need to calculate x1 1, right?
Yes, sir.
Because we have still not incorporated x1 in our calculations. Okay.
Yes,
So
sir.
now if you want to calculate x4 1, you can just pick up the third equation right here. Okay. This one.
Mm.
Because now we have exhausted 2 equations. We have a third equation right here, and we just pick it up and form an expression like this, right? X4 squared would be equal to 1 over 4 of 7 plus x1 minus 4x2 squared plus 3x3 cubed, right?
Yes, sir.
Okay, so just use this to calculate this another once more. For example, you can write 1 over 7 plus x1 0 because you don't have the first iteration value minus 4 x2 1 square. You already have this value plus 3 x3 1 cubed, right?
Yes, sir.
So just do a quick calculation with your calculator and let me know the value.
So it's minus 1105.06.
Minus 110 point
05 point.
05.
Sorry, sorry. Minus minus 1105 point
Okay,
06.
0.6. Okay,
Yes, sir.
so this
Yes.
will be minus and plus. Are uh uh are you sure? Really? Uh, I'm not sure. Maybe you made a mistake, I think.
Yes, sir. That is 7 plus 4.
No, no, no. This is still 0.
Yes, sir. X1 is 0.
Yes, and this is squared,
Yes,
and this
sir.
will be fine.
7 plus 0 minus 4 into that minus 4 is minus 4 square,
Yes.
and that plus minus becomes minus,
Okay,
and
this
then
one.
minus 3 into 11.33 cube.
Yes. Great.
Yes,
So
sir.
now, here we have a problem because our system was arbitrary. We had an arbitrary system here, so we got a negative value here. So this implies that the initial guess we took could be wrong.
Mm.
That would be x naught 0 would not be reasonable, or this entire system could also be inconsistent, right? So
Yes, sir.
inconsistent in the sense that if you tell your solver that, for example, 2x1 plus x2, you write it as 0, and you write another system as, let's say, x1 plus 4x2 squared equal to, let's say, minus 4 maybe. Okay.
Excuse me, sir.
Yes.
Sir, sorry, sir. I am running out of my data.
Okay.
So I couldn't able to watch this now, sir.
Okay. Okay. So no problem. Maybe if you want to leave, then you can do that. So I'll continue with another other things. So that's fine.
So can I get this on YouTube?
Yes, I'll be uploading all this.
So which channel, sir?
Those details will be shared to you soon. So I'm yet to
Yes,
upload the
sir.
first and second recordings. So you can do that.
Okay, sir. Thank you, sir.
So next time, if you have your remaining data on next Tuesday, then
Yes,
you can, if you want, you can ask some problems on your own. So because the live session was actually intended for the students, the course registrants to you know to ask problems for solving. So I was not really supposed to take up problems on my own and do that. Unfortunately, since we don't have many students who have registered for this course in the portal, so not many people are attending the live streams. So that's why we do not have a whole plethora of problems. So I'll be solving all these things by myself. So anyway, so that's fine.
I will
So
manage next my data, sir.
so if you can do that, it's really good. If you cannot, then obviously you can refer to the live stream. But I think that having a one-to-one session with your problems and your doubts and uh, live answer question answer sessions would be more helpful than watching the video, because watching the video is identical to what you are doing in the NPTEL course, right?
Yes, sir. Yes.
Yes. So okay. So good luck. Maybe if
Okay,
you
sir.
want to join next Tuesday, you can do that. Okay.
Yes, sir, I will join and also I will manage my data, sir, accordingly.
Great. Okay,
Okay,
bye.
sir. Thank you, sir.
Ah, anyway, so we do not have anyone joining us right now. That's unfortunate, but anyway, whatever happens, it doesn't matter. So anyway, so we could just take up this problem, the one that was discussed in the lecture. So let us write here as f1 y prime equals 4 minus 8y1 plus 4y2 minus 2y1 cubed equal to 0, and f2y equals 1 minus 4y1 plus 3y2 plus y1 cubed equals 0. Okay. And you are given an initial guess of 0.5 comes 0.5. That is y vector equals to 0.5 comes 0.5. Okay. This is basically the initial guess at the 0th node. So what you can do here is that let's obtain first, let's say we extract y1, or now this is something like you need to understand and ascertain your convenience. Okay, so you can extract y1 from one of these, or maybe we extract y2 from this one and we extract y1 from this one. So anyway, it won't matter much. This is y2, sorry. Oh yes, this is sorry, this was actually a time for you to solve the problem. So keep doing it. So there's no problem. Okay, forget this part since no one is interested in this one. We'll just get through this like that and we'll be solving the tank problem. We've got the tank problem here, okay? So what is happening here is that you have a hole of something like 1 centimeter in diameter. This is the symbol for diameter. And the diameter of the entire tank is 200 centimeters. Okay. And H initial is 2.25 meters. Find the emptying time. All right, so let's first understand the physics of this problem. So this is a classic example of mass balance, and I'd really appreciate it if you could, or we could just use a blue cell for blue water, right? Blue here and blue there, so it's all blue, so you know it's water. Yeah, let's do it blue. More blue. Yeah, perfect. Okay, so if you need to find the emptying time of this tank, what we first do is we apply a mass balance to the entire thing. Now, first, this interface of this, let's say there's air right here and air outside, and this tank is open actually. And this interface of air and water, here you have water, this will be going down at a certain speed. And let's call it h as a function of time. And the speed would be dht over dt. Okay. So this interface would be going down, the surface would be going down at a speed of dh over dt. But h is decreasing with time because as t increases, this tank will be this tank would be less full. That means it will be more empty. So H would continuously decrease. The level of water inside the tank would decrease with time. So that means that the speed of this water would be minus. Minus because the speed is positive at this point. Because we have already taken it to be downwards. If you had taken the speed to be upwards, then you could have a positive dh by dt would be giving you a negative value. So that means your answer would not be upwards, but downwards. Everyone's getting this point, right? Okay, so this is this speed. And now, use the continuity equation. For example, let's assume this is the entire control volume for, okay. Now this water is going from here. For example, the original volume for at t equals t is this, And at t plus delta t, it is this. Let me mark it with a red line. Beautiful. And you've already got everything flowing right here. Okay. So the amount of water that that is supposed to reduce the level, that is from ht to h of t plus delta t. The amount that is drawn from this tank is identically translated into what is ejected from this part, right? And let us suppose we are collecting this entire water into this tank. So in delta t time, this another tank would be filled with some water. And that would be identical to the amount that is leaking from here, right? So you could write that, let's assume this volume is V dot, okay? And let's assume this diameter, we already know it is, let's call it D. And let's call this one as small d. So we already know that pi d squared is the cross-sectional area of this tank into h, that is the entire volume of this water, into ht minus ht plus del t. This is the amount of water that is flowing outside. Would be equal to, let's call this pi d squared so and let's assume the velocity of at this outlet to be v out. Okay, so pi d squared into v out into delta t, because if you extend this, let's suppose you have this part, and wait, this position is at delta t, is at t, and at delta t, if you assume that it's just going straight right away, this much would be the extra volume of water that is being derived by emptying the tank. This is t plus delta t. And if you know the V out at this interface, you can always obtain V out into delta t as the length traveled by the fluid packet, by the amount of fluid that is being emptied along this cross-section, along this cross-sectional area. Okay, so what are the variables here? ht is a variable, ht plus delta t is a variable, and v out is a variable. So there are three variables, and you've got only one equation. So this system is obviously not solvable using the usual means. However, we have other means of solving this problem. What are those? For example, you write ht plus delta t as a Taylor's expansion formula, and you assume that delta t is tending to 0. Then you can write everything as dh over dt k times delta t plus d2h over dt squared ht plus times delta t squared by 2, of course, 2 factorial plus, and this goes on, but delta t is tending to 0. So as you increase the exponent on delta t to the power n, where n is greater than 1, will keep increasing. Will keep decreasing, I'm sorry. So in that case, the higher order terms could be conveniently neglected. So in all its entirety, you could always write that ht plus del t minus ht would be equal to dh over dt times delta t. Now substitute this part into this first equation. Let's call this first. So what you can write? You can write it as d squared minus dh over dt delta t equals to small d squared v out delta t. Let's just cancel out delta t, and you can do this because delta t is although it's tending to 0, but it's not equal to 0. Had it been equal to 0, if you try to cancel it out, then it would be basically an undefined problem, because you'll be, if you take this to the left hand side, then it would basically mean that you're dividing something by 0. So that you cannot define. Anyway, so you can write it here as dh over dt will be equal to minus d squared over d squared. We out. So this is the formula that you are getting. Okay. Now, we reduce everything into a single variable equation, into a two variable equation. So ht is also unknown, and v out is also unknown at the moment. Now, v out, how do you calculate the v out? Because calculating h is the objective of this problem. So you need to have v out for obtaining h. For calculating v out, we go to the physics of the problem. What does the physics of the problem say? Is this. The physics of the problem says that this entire thing, that's basically fluid inside the tank. And it's just going out right here. If you assume a single streamline originating from the surface of this entire tank of fluid, that's right there, then you could assume that if this is the point A and this is the point B, then obviously a single streamline can be identified to connect both of these points A and B. And let's say this is B stays right there, and this is A minus. Then maybe you can find another streamline that goes and converges like this. And let's say you've also got A plus. Then you've got another streamline that converges like this, okay? So in this case, in all these three cases, you've got particular streamlines. Here you've got the streamlines that actually can be connected to the endpoint. So that means the Bernoulli equation is valid here. And as soon as you know that the Bernoulli equation is valid right over here, you can just write it as B atmospheric, because at the surface we have exposed everything to the air, so we can simply write the pressure at the top surface at any of these points, A neg, A or A plus, as B atmospheric. And you also write it as half of rho v square. But what is v at the surface? At all these points, we've got a unique velocity, downward velocity, that is minus dh over dt. You can write it as squared, okay? Plus rho gh. This is h. And the gravity acts in the downward direction would be equal to if you connect both these points, then you can write PATM as a pressure at the bottom. Yes, it's since it is exposed to the atmosphere, it is simply PATM. And now you write rho times V out squared. Assume that the streamline is the particle at the end of the streamline at point B is moving out at a velocity of V out, because we assume a uniform cross-sectional velocity of V out throughout the entire outlet. And this rho g h, so h, that means the z from the datum. Let's assume this as z. So z equals to 0 here, and we ignore the length of the pipe. Okay, so you got L here, and L is much less than L. Okay, so cancel out the atmospheric right from both the sides, and then you've got also you could cancel out both these things. And you've got V out squared would be equal to multiply the entire both sides of the equation by 2. You've got dH over dt squared plus 2gh. Yeah, you've got this. Now, what you need is V out. You can write it as square root of 2gh plus dH over dt squared, right? So substitute this entire thing into this equation. So what do you get? Dh over dt. Let's call this h prime at the moment. So h prime equals minus d squared over d squared, that is small over large, and write V out as 2gh plus h prime squared, right? Now you can just square both sides, equal to d to the power 4 or d to the power 4 times 2gh plus h prime squared, right? I'll just perform some jumbling operations, mathematical operations. You could write it as h prime squared times d over d power 4 would be equal to 2gh plus h prime squared, right? Now you can write h prime squared would be equal to d over d to the power 4 minus 1 equals to 2gh. So how do you get? H prime would be squared equal to 2gh over d by d power 4 minus 1. Right? So if you want to find dH over dt, you'd be getting squared would be 2gh over, let's say it is d to the power 4 minus d to the power 4. And you've also got a small d to the power 4 right here. Just write it, just take square root both sides. Square root of 2gh, write d squared right here. And d to the power 4 minus d to the power 4 square root here. And you know, this could now you are taking a square root. This could be positive or negative, because if you've got something a squared equal to 4, then it could be plus or minus 2. So this could be plus or minus, but we, from the physics of this problem, we know that dH over dt is negative. So we'll keep it negative right here, okay? Now, this equation does not neglect. For example, you'd have often seen these equations like these formulations like they assume d is much less than d. But why should it be? For example, if you've got D as a finite, let's say a 2 meter wide surface area, a 2 meter wide diameter cross section, then why couldn't the whole be like this? It could be 1 meter. It doesn't matter. Yes. So one is not much less than two. That's wrong. So you cannot have directly like neglect D with respect to D and all those things. So yeah, so that cannot be done. Anyway, so let's keep this factor right here. And let's call this thing as dH over dt will be equal to minus 2 twice of gh, and multiply this entire thing divided by 1 over root of d by d to the power 4 minus 1. And let's call this let's call this part as kappa. Let's call this part a big K, right? We don't have any K here. So this entire thing becomes root of 2gh, right? So this is your final equation that you need to solve. And this does not seem really hard to solve, right? Because you could just use some mathematical manipulation. This is not even manipulation, actually. This is just basic things. So at t equals to 0, what is h? That is h initial. You need to know this beforehand, that's why it is already given to you. And at t equals to t, of course, at any time t, you've got h as ht. Now there's another alternative approach that you could follow. You could straight away integrate both of these equations like this as an indefinite integration. Square root of 2g over k dt. This would become as root 2 root h equals to minus 2 root 2g over k times t plus a constant c. Let's call it c1. Now you need to, insert t equals to 0 and h becomes hn. These initial value problems always require initial conditions. H initial, ini, let's call it ini. But this seems more elegant, right? So we'll be following this approach. So now you can write it as 2 root h t minus root of h initial will be equal to minus of root of 2g over k times t. So just write it as, yeah, so root h initial minus g over 2k square root of this entire thing times t. Yeah, because you take this 2 to the downside of this one, you become its 2 right here, and you divide both of these things, and it becomes square root of g by 2, and you insert the k inside, so this becomes this entire factor right here. Okay, now h becomes the square of this h initial minus square root of 2k squared t and the square of this. And that is reasonable, this would be something like at t equals to 0, you've got an height of h initial, but as t increases, this thing becomes the square of something that is less than h initial, less than root of h initial. So that means this entire thing will become less than h initial, and that is actually what's happening in the problem. Okay, so now let's calculate, k. You've got k as Yeah, we're back. There was some network issue, I guess. Okay, so this entire thing becomes h equals to root of h initial minus square root of g over twice of d by d to the power 4 minus 1. Hey, yeah, of course you've got a square here. Now, if you want to find, let's say, the emptying time, okay, then what you could do is that ht empty equals to 0. Just substitute this into this expression, and what you'd be getting is square root of h initial would be equal to square root of g over 2 k squared. Let's call it k again, and t. Or we could also do an interesting thing, we could write it as t squared, and you could write it as g by 2t over k squared, right? So this becomes, since the square roots are equal, the insides are also equal. Let's call this TEM for TMT. TEM right there. Beautiful. So TMT squared would be equal to 2k squared h initial divided by g. And TMT would be square root of 2 h initial k squared over g. So this would be the formulation for the emptying time. And this would actually become, for example, if h initial is given to you from the problem itself as 2.25 meters. 2.25 meters. You got g equals to 9.81 meter per second squared. And you've got d equals 2 meters. And small d equals 1 centimeter. Yeah, I guess that's the ratio. So, let's first calculate k, which is the geometric governing parameter of this problem. So what would k be equal to? K would be equal to d over d to the power 4 minus 1. So, in this problem, d is much, much less than d because d is approximately 1 over 200 times of capital D. So, although you cannot neglect anything in this thing, but you can always have something neglected in 1 over k, which would be d to the power 4 by d to the power 4 minus d to the power 4. This is approximately d by d to the power 4. Okay, so you can also write it as d by d to the power 4. That's because, this is something like 200, and you've got 200 to the power 4 minus 1, so it does not make really much sense to subtract 1 from 16e8, right? So T empty would be 2 times of 2.25 divided by 9.81. And what is k? K is 200 to the power 4 and you've got 200 to the power 8 and a square root of the entire thing. Now just calculate it, and you'll find that it turns out to be 9.81 multiplied by 200 to the power 8. What does this become? Wait, I guess we messed up. Right. Okay, so we made a mistake here. So k is actually, this parameter is actually square root of this entire thing. That is d squared, this is d squared. So this is d over d squared. So this is not 8, but 4. Or I could just erase it, the entire thing. Let's call it 4. Yeah, that's perfect. Power 4. And this is this is something like 27,091 seconds. This would become, if you divided by 3600 for your hours, you'd be having approximately 7.52 hours, which is approximately equal to 700 into 60 hours and 31 minutes approximate. Now, in the actual problem, they have straight away written V out would be equal to 0.06 of square root of 2gh. So the entire outlet velocity is really slow. So really low. So basically it is slow. So the slowness of this V out means that the tank would be emptied far later than what it would be emptied had the velocity been this one, right? So, well, that was the relationship that they gave out, so we cannot do anything. But anyway, through a proper mass balance, we've got this type of equation. Okay, so there is another equation that goes through like this one. So it goes through 2x y prime equals to y squared minus x squared. Okay. So what you could do here is that you can write dy over dx equals to, just keep the 2 here. That's a constant anyway. You can write it as y over x minus x over y. And so what you could assume is that you see the occurrence of y over x in 2 places, right? So what you could assume is that, let's say y over x would be equal to z. Okay. So you could write this entire thing as, or you could just, just wait a minute. Let me shift it all to the right side. You could write it as z equals to y over x. And that would imply that the z equals to x dy minus y dx over x squared. Right? So you could actually calculate, this becomes something like x squared dz equal to x times dy minus y times dx. And divide everything by x squared given x not equals to 0. Which is anyway not true because x equals to 0 is a trivial solution to this problem. So you could write it as dy over dx equal to 1 over x times dy by dx minus y over x, this entire thing. Yeah. Yeah, so this looks great. And this is z actually. So what you could write from here is that dy over dx would be equal to x times dz over dx plus z. Okay. So 2 times of x times dz over dx plus z equals to z minus 1 over z. And this becomes 2x dz over dx plus 2 times of z equals to z minus 1 over z. And this further becomes 2x times dz over dx equal to minus z minus 1 over z. Okay, so this becomes 2 times x dz over dx equals to a minus of z squared plus 1 over z. Z, right. So this would become minus 2z over z squared plus 1 dz equal to dx. Where we have just, multiplied both sides by dx into z divided by z squared plus 1. Oh, and you've got an x here. Yeah, don't forget the x. Yeah, and z squared plus 1. Now, you can clearly see that this is a simple problem of substitution right here. Okay, so assume that w equals to z squared plus 1. And you need to remember everything. So dw equals to 2z dz. And that's what you see on the upside, on the in the numerator, not the upside maybe. Okay, so this is dw over w would be equal to dx over x. And you can write this as ln of w would be equal to minus of log of x plus a constant term, of course. And you can write this entire thing as log of wx would be equal to c1. So let's keep it this way. And w is actually z squared plus 1. X would be equal to a certain constant, let's call it k, because this entire thing would become, if you find out wx would be equal to e to the power c1, and that is another constant. So a constant, e raised to the power of, e raised to a constant power would be another constant. And z, what is z? Z is actually y by x. So square the entire thing, multiply by x, and you've got a constant right there on the right hand side. So you've got y squared plus x squared divided by x equals to k. And this is the final answer. From here, you could actually calculate y squared pretty conveniently as kx minus x squared. And you could say that y equals to plus minus of kx minus x squared. So it's basically the equation of a circle. Write it as x squared plus y squared minus kx equals to 0. It's a family of circles with a parameter k. Where k could take any certain real value. and uh, the center of this equation would be of this circle would be what do you think it would be? It would be obviously k by 2 comma 0. And you can actually also calculate the radius. Maybe let's say if we assume k to be positive, then this would be k by 2. And the circle is, let's say, center right here. And it would also actually pass, if you put in x equals to 0 and y equals to 0 in this entire thing, so it will pass through the origin. So the y-axis is a tangent to this circle, always. So as you increase k, the circle would look like this. And if you take a negative k, it would look like this. And if you keep increasing k whimsically, arbitrarily, then it will just become like this. So it's a bunch of rings collected together. That's all it is. Okay. Yeah, that's great. So here it is. Well, it is just a circle, and that is exactly what they have also calculated it. And then yeah, so you've got another easy equation like this: dy over dx is equal to minus of cos x plus y divided with 3y squared plus 2y. Minus of cos cosine of x plus y, but it's 3y squared plus 2y plus sine of x plus y. Yeah, I guess that is how it is. No, so sorry, it's just cos both sides. Okay. Now dy over dx in this case is a bit complicated, so you cannot directly integrate it as it is. So you need to perform some sort of, trickery is right here. So you could say like, let us, you've got this equation and I want to solve it. So I'd give you 1 or 2 minutes maybe to think about how you could go ahead and solve this type of equation. Just 2 minutes, okay? And in the meanwhile, I'll make my secret jungle box. You don't look at it, okay? And I'll be solving it myself, trying to solve it myself. This is one of the reasons why I don't prepare, because so that it finishes off in the entire challenge if I prepare everything beforehand. Okay, so I guess no one did it, or maybe you tried but could not reach to the solution. So we'll do this really quick, and you assume that 3y squared plus 2y plus cos of x plus y. Okay. Now, how we'll be solving this equation is through the method of partial differentials. Okay. So you write this equation as crisscross both of these parts. Okay. So crisscross both of these, and what you'll be getting right here is mdy would be equal to minus. I'm sorry about that. No, ndy would be equal to minus of mdx. Yes. Now, so let us, if we could have some certain knowledge about, let's call that a function like, how do I tell you about that? X plus y dy mdy. Mm, yeah. Mhm. Okay, so the key is that, you know, what we want to ascertain is that, let's assume that there exists, we first find out del m over del y, and you find out del n over del x, right? So since here you've got x, so we'll be going with y with m, and here you've got y, so we'll be going with x with n. So del m over del y would be something like minus of sine x plus y, and del n over del x would also be something like minus sine of x plus y. So these both are equal. So this would mean actually that since the partial differential equations of both of these are equal, and this would be entirely a function. This is a function of x and y, and this is also a function of x and y. So what we could have here is that we have an exact differential formulation, right? This also happens in the heat conduction problems when you want to separate the variables into two parts. So what you do is that the left side is all a function of y and the right side is all a function of x. And you need to obtain both of them. So since they are that relationship, let's say f of x is equal to something like g of y for all x and y, then it is pretty obvious that both of these would be equal to a certain constant, let's say c. So this is the exact differential formulation, and then what you assume is that, let's say u is the integral of, you know, now you could write it as del m over del y is something like this. You define something like this, cos x plus y dy. Okay, so we are just integrating This is m dy. Okay, this would be something like sine x plus y plus a function of y, right? No, del u over del y would be equal to m. So you integrate it with that respect, and a function of, say, k or e, wait, del u over del x, you can write it like this. Okay, so I mean that if you got this certain something like this, then let there exist u such that del u over del x would be equal to m, and del u over del y would be equal to n. Now, if you've got this condition that uh, del m over del y, well, let's say del m over del y, you've got it something like this becomes del 2u over del x del y, and del n over del x would be equal to something like del 2u over del x del y. So you see both of these are equal, right? So if you got this condition that del m over del y is equal to del n over del x, then you can always go into this formulation. Okay, so this is the key. Now you can always reverse substitute these values into m and find it out like this. M is, cos x plus y, cosine of x plus y, you integrate it with respect to x plus y, plus a function of, let's say, f of y. Okay. So now you've also got del u over del y will be equal to n. So you just differentiate it with respect to cos x plus y plus df over dy would be equal to n. And what is n? N is actually 3y squared plus 2y. 3y squared plus 2y plus cos of x plus y. Both of these terms cancel out, and you've got df over dy equals to 3y squared plus 2y. So obviously f would be equal to y cubed plus y squared plus another c1, a constant, yes, since this is an ordinary differential equation, so there's no f of x extra, no extra f of x added here. Okay, so once you've got f, you can simply write u as sine x plus y plus y cubed plus y squared plus c1. Okay. Now, the original equation that you've got is dy over dx equals to minus of, this is m over n. Dy over dx equals to m over n. Minus of, okay? And now you can write it as something like mdx plus ndy would be equals to 0. And what is this? M is nothing but del u over del x times dx plus del u over del y times dy. Right? Which is basically just du. So this is how it is happening, Suppose you've got an equation like mdx plus ndy plus bdz plus, let's say, qdw equals to 0. Yes? And you can find a certain function, let's say gamma as a function of x, y, z, and w, such that you can write a small differential of gamma as del gamma over del x dx plus del gamma over del y dy plus del gamma over del z dz plus del gamma over del w dw. This is equal to 0. If you're able to write it like this, then you can just compare this form to this one. If you're able to find out these values, then your problem is done. So you just need to formulate du finally. And once you've calculated u in its entirety, then you can just write the final problem as sine x plus y cubed plus y squared plus c1 equals to 0. So this does not carry any significance. So this becomes sine x plus y cubed plus y squared equals to a constant term c. So this is the final form of the equation that you've got. So we'll be ending the live stream today. Already crossed 2 hours with plenty of time, plenty of extra time. So, okay, good to meet everyone, although people did not join today. That was unfortunate, but we've already recorded everything and we'll be putting it up on the YouTube channel. So don't forget to check it out and subscribe.